Hi everyone, thank you for coming. Before we start, I want to make sure if everyone can hear me. Can you hear me? Okay, great. So let's go over the topic first. So I emailed Dr. Bhatia and I received a reply from him saying that these are the topics that will be covered on your exams. So the first topic will be Rom-Based Design, and I will go over the basic structure of that. And the second will be Sequential Logic Elements, it's flip-flops and latches, and as well as the structure of that. And the last part will be analysis of sequential circuits. And we will go over things like shift registers, counters, introduction to state machine. And Dr. Bhatia also said that he will expect you to have the design of sequential circuits, but there will be no timing analysis. So before we start, is there any specific topic you want me to cover? Okay, so let's go over ROM. So ROM is the read-only memory, and it follows the AND/OR structure. And for the AND structure, the decoder is used, so that is not programmable. And but not being programmable means that you will not be able to simplify it using from the Boolean equation. You have to use it with the maximum terms. But however, the OR structure will be programmable. So right here we have a decoder. It's 2x4 decoder. And let's assume that our A as our MSB input and B as our LSB. And you will know that for address 0, A naught B naught will be the output of that. And for address 1, A naught B will be the second output. For address 2, A B naught. For the third one, AB. Let's assume we have an equation here. It is A naught B C naught or AC. So in order to approach this problem, we can see that this term and this term does not have all the variables in it, because we know that we need A, B, C, at least A, B, C in our Boolean equation for our output F1 and as well as F2. So in order to find the term B in our AC, we have to do the Shannon expansion. And because the reason for not being able to just do AC is because this is the AND structure here. And we know we're going to use because we have 3 variables, right? So this will be a 3x8 decoder we're going to use. So to expand this term, we have to do the Shannon expansion. Okay, so AC will equal to A B naught C or A B C, right? So from this expansion here, we can know that our F1 equal to A naught B C naught, or with A B naught C or ABC. And we do the same thing for F2. And because this is the same AC, there's no difference as this one. So we will be using the expansion we already derived. So this will be A, B, not C, or A, B, C. So first step to realize the ROM logic, we have to draw a decoder. The decoder, remember that it's not programmable because it's going to have a fixed output for the end structure. So we know the first address here, 0, this is going to give us an output of A not B not C not. This will give us A not B not C, A not B C not, A not B C, and so on. So let's take a look at our F1 first. So the way we're going to draw this is that we're going to draw a line that is going to be connected to the OR gate. And let's see our output, our equation for this. We have A not B, C not, A B not C, and A B C. So we can see this is actually 0, 1, 0. So this will be address 2. And this is 1, 0, 1. So this will be our address 5, I believe. This will be our address 7. So to make the connection, normally we just put an X at where it intersects. So address 2 here, and 1, 0, 1, address 5 will be here. And for 7, it will be right here. Now, we do the same thing for F2, which is our other output. So we have address 0, address 5 again, and address 7 again. So we draw a line across all the bus here, connect to the other OR gate, make connection at 0, 5, and 7. So we will have our output here, F1 and F2. So we can call this a 8x2 ROM because it has a total of 8 addresses, and we have a total of 2 outputs. And now there are several ways to draw the ROM, and the other way is to use the LUT and write it inside the component form. It's basically the simplification of the circuit above here. So we will see the LUT structure inside our ROM. And how we are going to do this is that we take the sum of midterm, and we know that F1 is going to have 1 at address 2, 5, and 7. So we look at address 2, and let's set the row to the column to the left as our F1. So at 2, 5, and 7, we will see that we have 1 filled in here, and the rest because the rest will be 0, so we filled in 0 for that. And however, for our F2, we basically have the same thing. We can see that it has 0, 5, and 7. So let's do this. 0, 5, and 7. So as you can see here, there are 1s filled into the corresponding position, and the rest will be 0. And the way this is going to function is basically the same. So assuming our A is our MSB and C as our LSB, address 0 will still be our A, B, A naught, B naught, C naught, and address 1, A naught, B naught, C. So that means when 0, 0, 0 is inputted, then our output F1 and F2 will select this address and have the output of 0 and 1. So now let's move on to realizing an example, the calculation part. So let's say we want to have a binary input, and the output we're going to be outputting the decimal value of our input square. So what this means is that if we have, like, take two variables as an example. If we have 0, 0, this is 0, right? And 0 squared is 0, so our output will still be 0. 0, 1 is our 1, and 1 squared will be 1, still 1. So, but however, 1, 2 will be, 1, 0 will be 2 squared, and this is actually going to give us 4. So we can see that this converted to binary value will give us 1, 0, 0. So to do this problem, the easiest approach is to first draw a truth table. And notice that this row to the left, this column to the left here will be our input, and the one to our right will be the output. So, and you might be wondering how many outputs we need, right? Because based on the inputs, the maximum decimal value we can get is 7 squared. 7 squared is going to be 49. So 49, we're going to need at least 1, 2, 3, 4, 5, 6, 6 outputs to realize each. The first one will be 2 to the 0, second one 2 to the 1, and the last one will be 2 to the 5th. So we can convert binary value to decimal value here. And let's work on, let's say if we have an input of, 0, 1, 1, and 0, 1, 1 is going to be converted to decimal value as 3, right? And 3 squared is going to give us 9. So we have to convert this 9 to our binary value so we can put it into our output. So it's not going to fit into 32, so 0 here, 16 no, 0, 8 yes, so we put a 1 here, 0, 0, and 1. So this is going to give us 9. And if you go to check the row here, we will get 0, 0, 1, 0, 0, 1. So this will be our output. So to implement this using the ROM, we know we have a total of 6 output, right? So we know the decoder will have is 3 by 8 because it depends on the inputs. And for the outputs, we need at least 6 OR gate. If you remember the structure we talked about earlier. So after filling this table, we want to look at the ones. So let's do the OR gate for output 0 first. We see output 0 has 1 here, 1 here, 1 here, and 1 here. So we can derive an equation where output 0 equal to A naught B naught C. If we look closely at our inputs, or with A not B, C, or A, B not C, or A, B, C. And after drawing our decoder, we basically follow the same thing, where O0 will be connected to, because we know this is going to be our address 1, right? This will be our address 3, this will be address 5 and 7. So we make a connection at 1, and the next one is 3, 5, and 7, and so on. And then we do the same thing for all of our other outputs. But however, if you look closely at O1, output 1, it's O0. So we actually don't need an OR gate for this. We can just connect this to a ground if we need other external circuit for this output. So we can see that because we still have 8 addresses, and we have a total of 6 output. Although we only have 5 OR gates, but we actually have this one as our output. This is going to be a ground. O1, yeah. So we can call this a 8x6 ROM. Okay, so this concludes our ROM design. Is there any question so far? Okay, cool. Feel free to stop me if you have any question. And let's go to flip-flops and latches. So let's go over the elements for to build our flip-flops and latches. Normally we build our flip-flops and latches using NAND gate and NOR gate. And in this case, I'm using a NAND 2 here as an example. If you look closely to your left here. So let's go over the output for the NAND 2. So we know the NAND gate with input of A, B into two input. For 0, 0, it's going to be 1. 0, 1, 1, 1, 0 is going to be 1. But for 1, 1, it's going to be 0. And look closely at this row here. And we can see whenever a 0 is going into the input, it's going to force the output to have an output of 1. So we can use this to our advantage. So we have our SR latch here. And to go over the definition for latches and flip-flops, it's actually really complicated because not many people have a absolute definition for latches and flip-flops. Some people said latches are flip-flops, and some people said otherwise. And for latches, we're going to define it as level sensitive. It's what UTD professors define this. And for flip-flops, it's going to be edge sensitive. And by edge sensitive, it means that it sends the rising edge or the falling edge. And for level sensitive, it's just going to sense either it's 0 or 1. kind of like an enable. Okay, so let's say we have S and R inputted into our NAND-based latches. So we can see that Q and Q naught will be 1. So in this case, it's going to be our undefined, because we want our Q to be the opposite of Q naught at all times. And let's say if we have 1 as our reset and 0 as our set, 1 is going to go into the NAND gate, but if we see the truth table here, 1 is not going to be able to determine the output of that NAND gate. It has to be dependent on the other input. So the easiest approach is that we approach from the 0 here, because we know 0 is going to force the NAND gate to output the 1. So for set, we know this is going to have an output of 1 here, right? And then 1 is going to go in this direction to the bottom NAND gate. So we see 1, 1 going into the bottom NAND gate is going to give us an output of 0. And usually we define set to be setting Q to 1. So I should flip this to Q and Q naught. And when it is reset, we know that it's going to set Q naught to 1 and Q to 0. So Q will be 1 in this case. Wait, no, Q will be 0. And now let's go to the next row as our 1 or as our 0. So we can see now that whenever there's a 0 input, so we want to look at R. So this is going to force the output to be 1 here. And 1 is going to pass through this path going into the upper NAND gate. And again, 1, 1 is going to give us 0 here. So we can see that it actually set Q to 1. Okay. So how about the next one? The next one will be 1 and 1. And because we know 1, if we input a 1 into our NAND gate, we have to be dependent on the other input to determine the output state of the NAND gate. So in this case, we actually want to look at Q and Q naught here, the original value. And let's just assume the original value of Q and Q naught is 1 and 0. So again, 0 going into the bottom NAND gate. So 0, 1, what's going to be 0, 1? 0, 1 is going to give us an output of 1. So as we can see here, it stays the same. And for the other, 1 is going to pass up toward the upper NAND gate, and 1, 1 is going to give us 0. So 0, it stays the same again. So we can say that this is our storage. Or we can write this as Q. And let's define Q to be our current state. And Q plus equal to next Q. So our next Q will actually be staying as the same value as our Q. So we call this a storage. And if we build, so same thing for the NOR gate based latches. If we use the NOR gate based, we have to erase this and say we are doing NOR 2. the output will be different. So we know it's actually the opposite of OR 2. So we know OR is going to be 0, 1, 1, 1, right? But for NOR, it's going to be the inverse, so it's 1, 0, 0, 0. So again, we see a pattern here. If we have an input of 1, it's going to force our output to be 0. So using the same idea, we will be able to trace the NOR-based latch. And to save time, I'm sure you already know how to do this based on the previous example. So let's move on to the next part. The next part will be JK flip-flops. So as you can see here, we basically add, well, there are several ways to derive the JK schematic for this, but the schematic we have here are using NAND. And we notice that there's a clock here, but this is called the JK flip-flop, but it's actually a latch. But most people call it a flip-flop because it's going to be level sensitive. It's going to be level sensitive. And so the truth table for our JK flip-flop will be 0, 0. Again, do the truth table. For 0, 0, it's going to be storage. That means it's going to be the same as its previous value. And for JK01, it's going to reset. So that means Q will become 0. And for 10, it's going to set Q to 1. And for 11, it's going to toggle. But for this one, it's not a complete flip-flop. It's a latches. Means that it is level sensitive. If you look here, the toggle is actually going to keep it toggling until it goes down to 0 here. And this toggling is due to the propagation delay. So if we are going to build a T flip-flop from this, it's actually going to be a really, really bad T flip-flop because it's just going to keep toggling until our clock goes down to 0. So basically we have to derive a new method for our flip-flop. And the idea is to use 2 latches and connect them together, but with an inverse clock. And by doing this, we have the advantage of having this to be edge sensitive. And it either is falling edge or rising edge. So we have, again, J and K here. And with J and K, we will be able to use it to make a D flip-flop as well as the T flip-flop. And J and K flip-flop is also called to be SR because it's basically having the set and reset function here. And for D flip-flop, it's actually called delay because it's going to wait for the clock trigger for the flip-flop to pass the value of D to its output. And for T flip-flop, it's toggle. And for D flip-flop, we basically connect an inverter from D to K, and then J will be connected to D directly. And how about for T? We simply connect 2 of the input together. So like this. So this will be T. So the advantage of using master slave, again, is that it has the edge sensitive function, unlike the level sensitive. So let's say we have a D flip-flop here and a T flip-flop. We know for D flip-flop, Q is going to take the value of D when the clock triggers. And for T flip-flop, we know when T is equal to 1 and the clock pulse, Q will become Q naught. And when T is equal to 0 and the clock pulse, nothing will change. And let's say we have a shift register with using D flip-flop. And assuming our initial D0 value is starting at 1 here, and our D1 is going to be going into here, which is equal to Q0, right? This is Q0. So as we can see here, assuming this is rising edge trigger, when the clock is going from low to high, it's going to trigger both flip-flop to pass the value of D to its output. So initially we have D0 to be 1, D1 to be 0, right? And Q0 is 0, Q1 is, let's say, assuming it's 0. So when the clock pulse, D0 is going to go through this flip-flop, and then Q0 will store D0's value. So we can see this will become 1. And because this is 1, then we know Q0 is going to be connected to D1. So Q0 equals to D1, so we know this will be 1 as well. But however, this is still going to be 0, right? Q1. The reason for Q1 to be 0 is because that initially it's D1 here, which is D1, is 0. So let's do more clock here. Now we're looking at this location. So we're going to set the input of D0 to 0 now and see what's going to happen. So when the clock pulse, D0 is going to pass to Q0. So we see Q0 is actually going to be 0 because of this location. And then D1 is connected to Q0, so this is going to be 0. However, for Q1, it's going to be 1. So why is it 1? You might ask, why is it 1 when this is 0? But notice that this is synchronized. So we have to look at the previous input value, which is this one here, D1. The previous input value for D1 is 1. So D1 is going to pass to Q1. As we can see here, this will become 1. And the next clock pulse is actually going to set everything to 0. Because we see at this location it's 0, so we know Q0 is going to be 0 for sure when the clock triggered. And then looking at Q1, because previously we have D1 with an input of 0, so this will become 0 as well. So to draw a state that's going through here, because we have initial input A1 to our D0, so it's going to shift right. So 0, 0 to, this is going to symbolize clock trigger. Zero zero going to 1 0, and then go to 0 1, and then go to 0 0. So at this point, is there any question you have? Okay. So then let's go to the analysis of sequential circuits. So previously we were given, so for our previous problem here, we actually did a little bit of analysis here, because basically we did Q0 is connected to D1 and vice versa. And then our D0 is just our input, and then Q1, both Q1 and Q0 are our output. So let's draw another flip-flop here. And let's say we have three flip-flops, so that means we will have 3-bit output. So assuming we have T flip-flop, and then we are given a circuit as shown below. Clock. And we want all of them to be synchronized, because they are going to share the same clock. So let's say we have, let's put a random AND gate here, and let's call this an invert. And let's call this T0, call this T1, and call this T2. And we're going to call their output as Q0, Q1, and Q2. Input as T1, T0, T1, and T2. So let's say we connect an input of Q1 going into an inverter, and then let's say we have Q2 here. And maybe we put a AND gate here again. Let's just put Q0 connected to T1, and this will be Q2. And let's say this is directly connected to Q1. So we want to know what's the sequence for this. So we know T0 equal to Q2 Q1 naught because of this here. And then for T1, it's equal to Q1 Q0. For T2, it's just going to be connected to Q1. So with this circuit given, the first step to analyze this circuit is to determine what's going to be the input for our each flip-flops. Okay, then once we know that, and let's set a condition, another condition, assuming Q0, Q1, and Q2 all equal to 0 initially. And we can start drawing our timing diagram. So we have our output as Q0, Q1, and Q2. And then we have a input T0, T1, and T2. And then we have the clock here. And then the clock is a given input, so that means it's just going to keep toggling. Okay, so the part I did not draw the line, that means that this will be, well, might as well draw it. So assuming it is rising edge again, well, let's do it falling edge to save the space. Assuming the flip-flop is falling edge, we can start by drawing each checkpoint. So we know initially Q0 and Q0, Q1, Q2 is R0, right? So this will be 0. So what is going to be our T0, T1, and T2? So in this example above, because T0, T1, T2 will always be 0 based on the schematic shown above, that means it will never have an output of 1 of any sort. Okay, so that was a really bad example. So let's say we have Q2 not and Q1 not. We invert this portion. Then we can see that T0 actually become 1. Okay, so I saw a question from Bob. Shouldn't T1 be Q2? Yes, you're correct. Sorry. Q2 and Q0. And so I'm not so sure what your professor is going to tell you, but if he doesn't tell you, then maybe you can state it to the professor, saying that assuming it is rising edge or falling edge. And so for level triggered, you will have to, because we know flip-flops is going to be edge triggered, right? And latches will be level triggered. So if the problem gives you flip-flop, you will assume it's going to be rising and falling edge triggered. If the problem says it's going to be latches, you will assume it's going to be level triggered. And if the professor didn't state whether the flip-flop is rising or falling, you have to state it for the professor and then do the problem. Yeah, so thank you for the question, and thank you, Bob, for correcting my mistake. And so let's move on to the checkpoint here. So at our first checkpoint, remember how we have to check the previous value. So we know T flip-flop is toggle. So when T is 1, T is 0 and T is 1, T is 0 is going to be the same. And this is going to become Q naught. You write this better. So Q plus Q next state will equal to Q previous Q, and then Q new state will equal to previous Q but invert. So for Q0, let's see. Because Q0 is the T0 flip-flop, so we have to check the input, which is this location. And we can see that it's 1, right? So when the clock triggered, it's going to toggle from 0 to 1. And then how about for Q1? Q1 is going to be Q2 ended with Q0. So that means our previous value is RO0. So our previous value are also O0, so T1 will be 0, right? Because T1 is connected to the AND gate with inputs of Q2 ended with Q0. So we know this actually still remain unchanged. And for Q2, we know it's connected to Q1, and Q1 previously is 0. So our T2 therefore will be 0. So this will be 0 as well. And after finding all the state here, this will be 1, 0, 0. So our T0 will now be 1 again, right? Because Q2 not ended with Q1 not is going to give us 1. And then for T1, this is going to be 0 because Q2 is 0. And for T2, because our Q1 is 0, so it will be 0 as well. And so we can already see the pattern here that T0 is always going to be 1 because Q1 and Q2 will never go to 1 because it's 1 for the toggle. So Q0 will keep toggling. basically divide the frequency of the clock by 2. Okay, so let's see. Yeah, to find a better example, you can play with this circuit yourself and then see if you can find any significant difference here. So let's say if we have Q0, Q1, and Q2, we will see that it's always going to be 0, 0, 0, 1, 0, 0, and then it's going to go back to 0, 0. So this is our sequence here. Okay. I just saw that I missed a question from George. Can you explain why all of them are 0 one more time? Were you talking about the D flip-flop, the shift register here? Yeah, if you're talking about this for shift register, because we know the value is going to keep shifting right? So that means 0, 0 is going to inherit the input value and having store 1 here. And because at this location here we already disable the input, so that means it's going to be passing 0, and then 1 is going from this left to right, so 1 is going to this location. And then when the next clock trigger, because our input is still 0, if we check the timing diagram here, so this will be 0, 0, going back to 0, 0, which is the same as the initial state. Okay, does this make sense? Okay. If so, after that, let's go look at this. So after analyzing this circuit to the left here, on the top, is there any question? Okay, thank you for your question. And anyone has any question regarding how to analyze the circuit given? So right now we have done shift register, and we have done some analysis of the sequential circuits. We have done the flip-flops and latches. We have done the Rom-based design. So now let's take a look at counter and how you can design them. Okay, so let's have a table here. Let's say we want to build a 3-bit counter. And we call it this A, B, C. And the idea of the counter is that we're going to have the count from, so let's make it count from 0 to 7. We can also have 0 to 4 if we want, but in this case, let's do 0 to 7. Well, actually, we can do 0 to 4, just to save some time as well as covering some basic. So the binary value for 0 is 0, 0, 0, 0, 0, 1 for 1, 0, 1, 0 for 2, 0, 1, 1 for 3, 1, 0, 0 for 4. And then we wanted to, once it reaches 4, we wanted to count back to 0, 0. So let's put 0, 0 here. And because for 3-bit counter, we know we are going to be required to have 3 flip-flops, right? So let's say the problem is going to restrict you to have only D flip-flop. So our QA, QB, and QC as our next state here. Actually, let's do the input here for D here. So D, DA, DB, and DC. And this will be our flip-flops output QA, QB, and QC. And doing from 0 to 4. So we can see that if we start with 0, we want our next value to be 0, 0, 1. So in order to do this, we have to look at it column by column, which means flip-flop by flip-flop. So let's determine the input for DA first. And remember that we're using D flip-flop. And in order for DA to go from 0 to 1, we know that our DA has to have an input of previous value, so which is A not B C. So when the state 0, 1, 1 is detected by the combinational circuit, the combinational circuit is going to input a 1 to DA in order for QA to become 1. I hope that makes sense. Yeah, so for D flip-flop, we want to look at when the values is changing from 0 to 1. That's when we will need to check the combinational circuit. And for DB, how about for DB? DB is going from 0 to 1 here. So we know at this location we wanted to detect A not B not C. as well as this location, because in order for D flip-flop to remain as 1, it has to have has an input of 1. So the previous value for this row, check here, is going to be A0, B, C0. And then we do the same thing for C. We see that C is going to 1 when A, B, C are 0. So we can put here DC will be A, B, C, not. And then the next state that is going to 1 is this one. So we look at this state here, and then we check the previous. We see that's 0, 1, 0. So we can put A0, B, C0 right here. So by doing this, we know that QA, QB, QC, let's say this is our previous state, and this is our next state. The next state from 0, 0, 0 is going to run 0, 0, 1, and it's going to 0, 1, 0, and this will be 0, 1, 1, and then 1, 0, 0, and then back to 0, 0, 0. So now let's draw the flip-flop. So I'm currently doing the test review right now. I cannot believe this. Give me a second. Hello? I'm doing a test review right now. Bye. Okay, let's get. So we have flip-flop. And let's say we have 3. Because it's a 3-bit counter, so we need a total of 3 flip-flops. So we have D here, because we're using D flip-flop, and Q, Q0. Call this A, B, and C. So based on the previous table we have, let me finish the combination first. So clock, and this is going to be counted to the same clock. So DA, DB, and DC. QA, QB, and QC. So from the previous table we actually need to start making the combinational circuit in order for it to stay in the correct sequence. And to do this, we see here for DA. Let's do DA first, because DA is going to be required to have an input of 1 when the sequence of 0, 1, 1 is detected. So we have A0 and B and C. So we are going to have an AND gate here, and the previous value will be stored in QA, QB, and QC. That means This here will be connected to QA. This here will be connected to QB. And this will be connected to QC. And notice that QS is going into an inverted input. So what that means is that it's going to give us QA, not QB, QC, going to DA. So the table below was above was a bit confusing because this should be QA, QB, QC. Yeah, and we can move on to the next portion. So our DB is going to have two possible midterm. So that means we will require to have a OR gate connected to DB. And DB is going to be connected to A not B not C and A not B C not. And for DC, again, we have two midterms, so we have to have a NOR gate. And we have A not B not C not, A not B C not. Yeah, I keep writing A, B, C. This is actually QA, QB, QC not. But I'm sure you know what I mean. QB, QC. So this is how you're going to design your counter and any finite state machine, actually. And because the professor is not going to ask you to have the timing analysis, I'm not so sure if you want me to do the timing diagram for that. If you want me to do a timing diagram, please say so. And let's stop here for a second and see if you have any question for this method of designing. Any question? Okay, so the problem for this one is that we're limited to only be using D flip-flop. So what if the problem is going to ask you to derive the counter using T flip-flop instead? So for T flip-flop, let me erase this. Okay, so I should erase this portion as well because it's not going to help you understand this any better. And so let's say we have T flip-flop. So we know T flip-flop is going to toggle only with an input of 1. So what that means is that instead of checking when it does go to 1 for T flip-flop, we have to check when it toggles. So we know at this location here, it's going to toggle from 0 to 1. And this location as well is going to toggle from 1 to 0. So what that means is that we're going to check 2 previous state here. So for our 0 to toggle to 1, we have to check this state, which is A not BC. So when this sequence detected, it will actually send a 1 to the input of TA. It's going to send 1 to TA. And in order for this portion, for 100 to toggle, for A to toggle from 1 to 0, it's going to have to check the previous state again, which is A, B, not C. Then again, it's going to give a 1 to TA. Then the clock pulses is going to pass to change this into this one. So we see we have done TA. And how about B? So TB, we know it's going to change from 0 to 1 in this location. So we can write down A not B not C. And then if we check here, 1 is actually going to stay the same. So we want toggle to be 0 because we don't want it to change. We don't want it to toggle back to 0, right? So let's see. The next one, this will change from 1 to 0 at this location here. So this is our previous value. So we can see it is A not B C. So any changes for B? So no more changes. That means we can move on to C. Now C is going to change from 0 to 1 in this location. So we need to toggle at that location, as well as this location from 1 to 0, and then as well as this one, as well as this one, right? So we check the previous value. So we get A, B, C, all invert. So A, B, C, invert, right? And then so after the clock pulse, we will be able to get this. And in order for C to go from 1 to 0, we have to make a toggle again. So our previous state is A not B not C, looking at this case here, and then our previous state. How about the next one? So we have done this already, right? So this will actually become the previous state for this one. So we will see this A not B C not. And looking at this, in order for it to go from 1 to 0, we have to look at the previous state again, which is this row here, which is A not B C. So we will be able to draw the circuit, counter circuit, using T flip-flop. Okay, so this is our TA, TB, and TC. This is QA, QB, QC, clock. So A, B, C. So we know, looking at the table we have here, we will see TA actually has two midterms, so we still need an OR gate. With AND gate, and to save time, I'm just going to skip drawing the AND gate. It's going to be A, B, not C. So we know the output here will be TA. TA will receive A, not B, C, or A, B, not C. And then we do the same thing for other part. TB equal to A, not B, not C, or A, not B, C. TC will equal to A not B not C not, A not B not C, B C not, or A not B C, right? So the really fun thing for this is that we can actually simplify the equation if it gets too complicated. Like take this one for an example, right? We can factor out A not C, and it's going to be B not or B, so this will become 1. So TB can actually, the input into the TB can actually be simplified into AC. A not C, I mean. A not C. And then we can do the same thing for this equation here. We will get, it's going to be A not B, factor out C not or C. So this will be 1. So A not B, so, and then we can actually do the same thing for this one as well. So this will become A not B not. So after doing the Boolean algebra, we will get A not B not or A not B. And we can see that we can simplify this further again, which will be A not B not or B. So this will be A not. So we can actually tie this to A not. So I'm not so sure how in-depth your professor is going to cover the design of sequential circuits on your exam. But once you master the idea of this table here, you can basically do anything. It doesn't really need to be a counter, because we know counter is going from 000 to 001, and then it's going to follow the same pattern, right? But once you master the table as shown to the left here, you can actually easily derive a sequential circuit with a random sequence. Like we can go from jump from 000 to 00 or something. Maybe it goes to 01, something like that. So is there any more question for this topic? So this may seem a bit confusing, but once you practice enough problem, then you will have no problem at all. Any question? And I'm wondering if you want me to cover Verilog using the model. So I know that it's more for Dr. Norami's class, but I'm not entirely sure if Dr. Bhatia is going to expect you to know how to code. And if there are no more questions, then we can call it for a day. Okay, good to know, Bob. Thank you for your reply. Any question for what we have covered so far? So basically, we really just did the introduction to finite state machine and counters as well, and as well as shift register. Covered this as well. So if there are no more questions, then let me switch to something. Good luck on your exam.